in this webinar. So as Larissa said, I'll start by defining a bit what Anycast is. The first thing one needs to realize is that Anycast is above all a routing scheme, a routing technique, not so much something you do to the servers. Though for things to work smoothly, you have to be aware of how this works in order to configure the servers properly and to have a good service running. This actually points to something that Eric will point later. There is a need for cooperation between the network side of the house and the system administration side of the house whenever they are separate for this scheme to work. So we're going to go through a quick overview of the routing schemes or the types of traffic that you normally come across on the internet. You have the client machine, the red dot on the left, and the cloud of machines, the yellow dots throughout the network. The most common type of traffic that you come across is, of course, unicast, the one that we are used to when we browse the internet or send mail. Our machines connect to a remote machine and only to that one, and the exchange of traffic is between those two machines. When you have a LAN and local area network, typically an Ethernet, you can also have broadcast traffic. Typical case of this is ARP, where you find out who has a given IPv4 address in your local link. And you do this by sending a message on the network that's listened to by all the machines on that network. An intermediate position is what we call multicast, whereby one machine sends one packet out into the network, and a series of machines that have chosen to subscribe to a particular multicast group will get copies of that packet. But still, the originating machine only sends one packet out. And then there is the subject of the webinar, Anycast. This is a slightly unusual type of traffic that you see compared to what you see normally, whereby you still have one originating machine and one packet goes out. And it reaches only one machine, but which machine gets hit from a pool of machines out there that shares the same public IP address is determined by the routing system, not by you and not by the receiving machine. The routing system will have several different ways of getting to the green points, and depending on where the right point is, it will select the best path to reach a machine that provides the service. Now, next, closest, in this sense, it means network topology closest, not necessarily geographically closest. So keep that in mind if you ever deploy these and observe unexpected behaviors. Normally, they both coincide, particularly if the network is all handled by you. But in some cases, depending on the topology of the network, you might end up at a place that's farther away than you might think. Still, the important part is that the packet is delivered and the service is also delivered. So, properties of Anycast, as I said before, each individual packet is sent to an Anycast IP address, an address basically that is shared or configured in multiple different servers across the network. And they get there through different pipes, through different ISPs even, as determined by the routing system. And the routing system, as I said, determines the best path in terms of network metrics, of network topology. One thing to keep in mind is that whenever you use Anycast, whenever you share an IP address between several different machines out there, you also need to give each of the machines a unicast IP address, a normal IP address that can identify each separately. Otherwise, if you try to monitor or log in or administer these machines and you target the Anycast address, you'll never know which machine you are connecting to, and that's not a happy situation to be in. So if you want to like SSH into a machine, you would SSH into the unicast IP address. So some use cases of how this is used, we normally distinguish between local and global Anycast. They are basically the same, use the same concepts, except the protocols involved are slightly different. When we talk about local Anycast, we talk about Anycast inside a network that you control, that you administer. And therefore, normally, what you use in that network are IGPs, internal gateway protocols, of which the two typical ones are OSPF or ISIS. It could be done with static route maps, However, that's not a good idea, because in the event of having a static manually configured setup, and if you have one of the servers go down, then you also need to go and change the configuration manually so that packets are not delivered to a server that is down. If you use the dynamic approach, the OSPF or ISIS, then this is all taken care of by the system automatically, assuming you set it up correctly in the beginning, or you bought an appliance that does that for you. The basic concept here is that routers are told to enable something they call equal cost multipath, where a router is told of different ways to get to the same IP address, and they all have the same cost in terms of the network. And when faced with something like this, what routers do is they round robin where they send packets between the servers. Now, there are two ways of doing this. The bad one, which is packet-based, and the good one, which is flow-based. When you have flow-based, basically what you have is that the router computes a hash based on the source IP port, IP address and port, and destination IP address and port, and it makes the distribution of load deterministic. So if you were talking, if a given client was talking to server 1, it will continue to talk to server 1 for a given service, and that's a very nice feature to have. When we move to global Anycast, basically what you have is Anycast implemented at the scale of the internet, and therefore networks that you do not control, different ISPs, perhaps in different sides of the world. In that case, instead of using IGPs, what you use are EGPs, and in particular BGP, which is the one that makes the internet go round. The idea is still the same, that these servers announce their IP address towards the ISP where they are hosted. This propagates through the internet. The different ISPs, the different routers throughout there figure out a topology for the network and deliver the packets to the closest network point. Most popular things to Anycast, I've listed them there. The most typical one by far is DNS, both in the recursive and the authoritative sides. Recursive server for DNS are Anycasted normally in the local network, so they use local Anycast because normally you want your recursive server to address only your customers or your users, not the rest of the internet. You don't want to get into trouble for that. Whereas the authoritative servers are meant to publish the address of, for instance, your website to the whole internet, so they address the outside of your network, and therefore Anycast there tends to be used on the global level with BGP. And another protocol that's often Anycasted is NTP, the Network Time Protocol. It also serves a number of characteristics with DNS that make it particularly suitable for Anycast. And then some part of HTTP could be Anycasted as well. We'll talk about why this is not usually the case for generic HTTP, but for HTTP redirect servers, those things that basically catch up URLs and send you to the right place, it's possible to do it. If you have RESTful websites, this would also work. So let's focus now on the DNS and Anycast. DNS is particularly well suited for Anycast for two main reasons. One, the default transport for DNS is UDP, and UDP is a stateless protocol. There is no state stored in either the client or server, which makes it very resilient against any topology changes that might happen in the network at any given point. They are also very short transactions. DNS transactions normally involve one packet going out to the server with the question and one packet returning back with the answer, at least in the generic case. When you have TCP, you have a few more packets. You need to at least complete the TCP handshake. You can, of course, use the property that allows you to transport data already in the handshake, which shortens the transaction. But even using TCP for DNS, the transactions are still very small. They span a very short time interval, and that makes this work particularly well, even in the presence of network instabilities, because your time window to get things done is very short, so you are pretty unlikely to get any affected by any instability, and that's something that's fundamental to DNS. Of course, there are longer-lived TCP transactions, namely zone transfers. If your zone is very big, then you might see, and you have an unstable network, or the internet is having a bad day, you might see some instability that affects zone transfers. But that usually is only an issue with very big zones, not with most of them. So here we have an illustration of what how this would work in a normal network. You have several users hanging from different POPs and connected to the internet through a backbone, could be your own or the internet at large. And you have two regional hubs of servers serving DNS normally. In normal operation, without the red cross on the left side, users from POP 1 and POP 2 would go through the regional hub on the left and be directed to the servers on the left. And whereas the users hanging from POP 3 and 4 would go to the regional hub on the right and get service from the servers on the right. One nice thing about this whole Anycast is that it basically lets the routing system do its job properly. So if the servers on the left, on the regional hub on the left, suddenly were to have an issue, or had some scheduled downtime for maintenance, for instance, then the routes would disappear from the routers. The routing system would regenerate its table, get its new topology, and packets from the users in POP 1 and POP 2 would just end up going to the regional hub on the right, without the user having to reconfigure anything, without any system administration intervention or anything like that. Most of the time this actually happens without anyone noticing anything at all, which is a very nice property. This works at all geographic scales. In the case here illustrated, for instance, we have someone in Los Angeles trying to access normally a node in San Francisco, but for whatever reason the San Francisco node suddenly becomes unavailable. The routing system reconfigures itself automatically, as it does day in and day out on the internet, and delivers the packet to one of the next best, so to speak, server available. In this case, the red arrow is redirecting traffic to Chicago. In practice, to be quite frank, if the router has any smarts in it, it should deliver the packet to Atlanta, since the packet's already going through it. But it's just an illustration of how failover occurs without any user or system administration intervention. When you have multiple networks, things are a little bit outside of your control, but this is just normal routing, and we know that it works because the internet works day in and day out again. And what this allows is for local traffic to stay local. So Asia traffic stays in Asia, and if you have nodes in Asia, Anycast nodes in Asia, European traffic would stay in Europe, and the US would stay in the US. But in the event of any transatlantic problem, for instance, traffic would be automatically redirected, and again without any external intervention. So to summarize, Anycast is basically a routing scheme. It works in conjunction with how you deploy your servers and how you configure the routing system for the packets to be delivered. So you need collaboration between these two parties if you are not the one doing both sides. You need to understand which protocols are suitable for being Anycast and which ones are less so. DNS is a particularly good fit for this technique. NTP is also a good fit because it shares most of the properties that DNS has, UDP transport, short transactions. And it's very popular, and increasingly so. We at ISC use Anycast throughout the world. We provide even internet root DNS service using Anycast, and have done so for 12 years without a hitch. So don't be afraid, just be aware. And that's the end of my part. I'll now pass the baton to Eric Wagner, VP of Sales and Marketing at TCP Wave. Thank you.
DNS, or a set of servers that are partitioned out that run other applications. And this way they don't have to manage and update every server in their network, and they can stay better focused on the DNS servers. Some have dedicated the DNS server, or dedicated servers to run DNS only. This eliminates any risk of conflict with other applications. Most we find have contracted some sort of company to manage the BIND DNS service so that they get the latest updates, patches, things like that. And we found that most of them have some sort of homegrown routing protocol that they developed themselves, some disaster recovery features. The common challenges with a lot of these organizations are the risk of a black hole. That happens when routing does not shut down when BIND is not responding. So the routing protocol can recognize when there's a problem with the server, but it may not recognize when there's a problem with the software. Additionally, monitoring has become challenging when multiple sources are advertising the same IP addresses. If a DDoS attack brings down one Anycast device, there's a concern and a risk that the attack will migrate to the next one. Many of the businesses we talk to find it challenging to configure Anycast routing correctly. So moving on, we have now the case study of one of our current customers. It'll illustrate the challenges that we've seen and what we've done to resolve them. The original DNS configuration was 100 servers at the cache layer dedicated to running an ISC BIND DNS network. The DNS service was provided by one of the larger DNS companies, so they had a third party providing the latest updates and patches. They created their own routing schemes to have some redundancy, and they added some DER features to help improve resiliency. Some of the challenges that they faced were that the servers required system admin management and frequent OS patching. This was costly in both money and in time. They had a lot of patches that they were doing at 2 o'clock in the morning on a Saturday night or a Sunday, which oftentimes they would have to roll back when the patch didn't work. They also had limited dashboard management that came with the products that they purchased, and they were cumbersome, so they really never learned how to use them, and hence they never did use them, so they were not managing their network correctly. There was always confusion between the 3 different vendors. They had a server supplier, a DNS management company, and a separate routing group. None of them knew the other person's language, if you will. And there was a risk of DNS black hole due to the fact that the routing design was unable to recognize when there was a DNS problem or any kind of software issues. The disaster recovery plans were complicated, and only a few employees understood what to do if there was a problem, so that as they lost employees or changed headcount, they sort of lost their DR plans. They tried to add F5 as a load balancer, but that ended up being too costly, so they decided to walk away from that idea. And finally, they realized there was a lack of DR features and a lack of visibility should there be any kind of DDoS attack or a bug. The solution that we were able to put together was by having one vendor for the whole DNS network, which includes routing, the servers, and the appliances, and the DNS software, of course. They were able to reduce the costs and eliminate finger pointing. By hardening the operating systems, we were able to reduce the patches from 2 a month to 2 per year. That ended up being a huge reduction in patch management, both cost and time. We customized the SNMP to work with the existing dashboards and charts, which meant their NOC team actually used these charts for performance management because they were the same charts and dashboard that they were accustomed to using for their other appliances or their other servers. We added smart monitors called watchdogs, and this is a differentiator. These watchdogs are able to confirm the health of all the software as well as all the servers. If there was a problem, the watchdog would notify the NOC and try and restart the software to fix it. And if that didn't happen, it would take itself out of the network and therefore not create a black hole. All this was done automatically, and that's configurable by the client. We also use watchdogs to trigger automatic disaster recovery features. For instance, we added a second diverse DNS software to back up BIND. Then we leveraged the watchdogs to automatically toggle from BIND to the backup DNS as soon as there was any kind of problems detected. And of course, we leverage Anycast self-healing rerouting benefits, but here's where we can differentiate ourselves again, is we add the watchdogs to Anycast, where we're able to eliminate the chance of a black hole by rerouting the traffic when the watchdog found any kind of problem. The routing protocols were able to detect the server problems, but they were not able to detect the software problems until we added the watchdogs. The watchdogs can automatically react as well based on whatever the client wishes. Oh, you're still back one. Sorry about that. Additionally, we had the watchdogs reduce the chance of a DDoS attack by monitoring the DNS requests and automatically shutting down the offending IP addresses that were attacking the appliance. In other words, if the appliance was able to recognize when a DDoS attack was happening and react immediately. If a group of hackers try to take out a DNS server or hijack a website with a flood of DNS requests, your appliance will be able to recognize the offending IP addresses and black hole them automatically. When the risk of using Anycast, one of the risks of using Anycast with the DNS is that the DDoS attackers can take out one server, and then the Anycast will automatically reroute that traffic, that attack traffic, to the next healthy server in the routing scheme. And then this way you kind of have a cascading effect. So what the watchdogs were able to do was eliminate that risk by blocking the offending attackers before they were able to shut down any of the appliances. So there was no cascading. Finally, for our customers that have created a separate cache layer, we have the option of making the cache servers, or the cache appliances, automatically change over to a master server when there is a WAN outage. For instance, if Hurricane Sandy isolates a cache server in Long Island, it already has its own files ready to go and can immediately become a master server until the connections are reestablished. Lately we've found that a lot of our clients prefer using TACACS as a secure way to log in. TACACS allows the users to have one secure login location for all appliances, making it easy to change, eliminate, and add new users. In other words, when an employee leaves, you don't have to eliminate his or her username and password from each and every server. Instead, you can make the change once, and it'll cascade out throughout all the appliances. Once logged in, the users have either read-only access or they can be set as privileged users to many different levels, including root access. And then, of course, one of the benefits of TACACS is it does keystroke logging. So you're able to record every keystroke made by anyone that logs in so that if there is any problems that were done by somebody who logged in, it's a great opportunity for a training session, or if there was any kind of espionage or any disgruntled employees trying to take down a server, you would see the evidence of that right there. So keystroke logging has become important for most companies that are doing e-commerce or in the banking industry where there is a risk of some kind of attack within. Case study summary. For all medium and large businesses, we recommend code diversity. By having two flavors of DNS coupled with watchdogs, you can have backup DNS kick in automatically if there is ever a problem with BIND. Now, most of our customers prefer BIND, and BIND works great, but nothing is 100%. So this way you can back up with one of the lesser-known DNS providers, and there's a few of them out there, but you can choose one of those to be the backup DNS provider. Second, by leveraging enhanced Anycast routing, again, coupled with watchdogs, you can improve the resiliency by knowing when to automatically reroute traffic. We also recommend to our clients to leverage the watchdogs to notify the NOC when a problem does exist and automatically react so that there is no downtime. This works best when coupled with customized tool sets so that your company will see, using their dashboards, will see when there's a problem. One more thing to add is by moving from a server model to an appliance model, we can eliminate most of the sysadmin tasks, thereby reducing the total cost of ownership. Essentially, it's a hardened image or a lockdown image, so that if you need to, we can just reset your image should there be any problems. Yet we still give you the flexibility to log in and make changes yourself as well. It's not a black box solution. It's sort of the best of both worlds for both of those options. Go into the next slide. This page is more or less our marketing pitch, so I'll move off it as quick as possible. We customize DNS solutions. We can improve disaster recovery by leveraging Anycast technology coupled with watchdogs, and we improve resiliency by increasing visibility through your NOC, and of course with software diversity. And then finally, we can reduce the total cost of ownership by leveraging the appliance model versus a server model. The next couple pages are the sample fault management reports, and I'll slide through these very quickly. I don't want to put you guys to sleep. These are the type of reports that we can customize based on what you think is best for your NOC, but they're the kind of things where you can really drill down on any one appliance or even users by clicking through some of the highlighted buttons. And the last one here is some of our charts that are oftentimes used for network management, so you know what kind of traffic is flowing where. You can, A, confirm that the Anycast is working correctly as designed, and B, you can see where you might have some traffic problems and have to make some changes. And finally, the discount offers on TCP Wave appliances. To anyone that registered for this presentation or downloaded the recorded version of the presentation, we'll offer a 20% discount to the TWC DNS appliance, and that's valid through the end of the year. That includes customization and the first year of annual maintenance free. And now, Larissa, I believe I hand the control back to you. Is that correct?
Yeah. Yes. Thank you so much, Eric. That was really great. So, yes, I just wanted to go over one more thing, which is to thank Eric and TCP Wave so much for that information, and then to let you know about ISC's special offer that we have as a thank you for attending the web seminar today, which is a discount on training sessions or consulting services. At ISC, we have training sessions on DNS, which do go over some of the topics addressed in this course and a lot of more basic DNS, as well as we have an advanced DNSSEC topics course. We have an IPv6 course as well. And then we also have a 10% discount on our consulting services, and you can get information on both of those kinds of services on our website, isc.org. And I noticed that we have quite a few questions, so I'll just go through these and call out João or Eric, or take them myself if they're more in my line. It looks like Eric is answering one online already, but we'll go back through that. So the first one I saw was toward the beginning of the session, and I'm just trying to locate it. Okay, this may have been partially answered by the slides, but if you could go over it once more, João. It was a question about how load is distributed via Anycast. Would it be round robin or QoS or something else?
Sure. So basically, it's not exactly round robin in the way that we are used to DNS round robin, where you circulate through different IP addresses through the set of possible answers. What happens here is that the client will send the packet out into the network, and the routing system that's in charge of delivering that packet to a server will select which server, from its point of view, the one that's closest. So if your ISP has an Anycasted server for, let's say, .com, that query for .com would stay within that ISP, and it will stay always within the ISP. It will always go to the same place as long as the server is available. So it doesn't jump from one to the other, basically. The one you reach is the one that's closest to you at any given time.
Okay, great. The next question I see is also for João, and it is, are there any issues with Anycast related to DNSSEC?
No, there are no issues whatsoever. DNSSEC only makes packets a little bit bigger. Probably you need more than one to transmit the entire response, but because the server that is selected for a given client is actually deterministic, unless you have a really unstable network, which is not the normal case, there is no impact. And this goes for DNS with and without DNSSEC.
Okay, great. Can you share any useful troubleshooting techniques for Anycasted DNS servers, since you may not be able to easily identify which server is responding? I think that's also for João.
Well, I guess yes and no. I mean, if you are using TCP Wave products, they have their own troubleshooting techniques included, which are made easier. If you are, for instance, trying to debug someone else's Anycast service when you are having issues, what we have, the most useful technique people use is, I don't know if people are familiar, but BIND can actually, you can ask BIND a given question, a special question, that will get BIND to tell you which server, what's the name of the server. There are two types of queries that like that. One gives you the version of BIND, and the other one gives you an arbitrary label that the server administrator configures. When we do unicast, we give a specific label that's different to each of the servers. Normally we name them according to the city where they are hosted. So if you have any issues, you issue a DNS query, with dig or NSLOOKUP, any of the usual DNS debugging tools, and you get back an answer from BIND. It also works with other name servers, by the way, that tells you which machine are you talking to, and that gives you an idea of whether you're having problems with a given part of the world or not. That's really the most useful debugging technique if you're doing it by hand.
Okay, and this next question, I think actually probably really either of these that last one or this next one could be for either João or Eric, but this one is from Tal Ben Eliezer. It says, how does a slave bind server become a master on the fly without modifying configuration?
This is
right
Eric.
now you cannot.
Go ahead.
Sorry, Eric.
Go ahead, Joel. You go ahead and take it.
Well, in standard bind, there's no way, but I'm sure that probably your appliance can deal with that.
Yeah, we found a way where we do some prefetching, or we download the files so that they can have them ready to go already in the appliance, and then the watchdogs will recognize when there's a connection disconnect and automatically switch it over to a master server. So while the files aren't up to date minute, obviously they were probably downloaded, let's say, at 4 a.m. At least it's better than having a dead server that can't connect to anything other than its cache at the moment.
Okay, thank you both. And then I have one more question and then the follow-up on an earlier question. The first question is, what is the dig query for retrieving the server label?
Okay. You have to specify several options, or rather more than one term for dig. Normally, DNS queries go in the internet class. The dig query for this specific label is in the chaos class, which is abbreviated CH. The record type is a text record, so TXT, and the label is bind.name.
Hostname.bind.
Name.bind, sorry.
Hostname.bind.
Yeah.
Right. Okay. That's what I was thinking too. It's okay. We know these things, but we don't necessarily use them every day. The last are two comments about load distribution via Anycast, which Rhonda had asked about earlier. And she said, so the routing picks the closest route, but if that server is loaded down, it doesn't really load distribute. So is there a way to do load distribution beyond the routing method with Anycast? And I'll let you take it.
I think Eric's appliance, TCP Wave's appliance, deals with that out of the box. If you just have plain bind, then you need to put something around it. Yeah,
that's also what I thought. And then there's one more question, which is actually one that we also had this morning. It's not off topic, David. Is Anycast supported in IPv6? Does bind support it, or is it a non-issue? And João can go into this more, but I think the answer is it is supported and it's not a non-issue.
Correct. This technique, Anycast, as we described, is supported as well in IPv6. One note I would like to make is that when IPv6 protocol was defined 12 years ago, or thereabout, it included the concept of Anycast in the protocol itself, but that never got used. So that IPv6 Anycast that you find in textbooks is not what is being used. What's being used when we talk about Anycast, also on IPv6, is what we described here. It works the same for IPv4 and IPv6.
Right. Excellent clarification. Okay. I don't see more questions. I'm going to give it 1 second here just to see if anybody is still typing. Rich has provided the a configuration sample for using dig to get the hostname, hostname.bind.
Hostname.bind.
Yeah, and then we do have one more question. This is for Eric. TCP Wave, do you also monitor route tables for routing changes?
Yes, we do. I actually have one of my engineers, Patty, to see if there's any other. Is there any follow-up to that?
Yeah, we do, and we talk to the Cisco routers via SNMP.
Okay, and then we have a question that is, it's related, which is a BIND 10 question. I'll point this one at João. Will BIND 10 support multiple masters or master failover?
Okay, that's an interesting question.
I'm sorry to be mean and pointed at you.
Related to this webinar, but I'll give it a shot anyway. The answer is yes, but not immediately. One of the things we have to be careful about when telling people that we support multi-master is defining exactly what it means. There are DNS servers out there that by other vendors that claim to support multi-master, but it's not exactly clear what happens when you actually need to use that feature. For instance, if you have two servers serving a zone and the network becomes partitioned, one cannot talk to the other. And there are local updates, and perhaps some of them conflict because the two updates to the same resource were performed by different machines when the network is partitioned. What happens when service is restored? And there are various solutions for that, and I think basically when we have discussed this at the ISC, we are converging towards providing user choice rather than being aggressive about it and dropping everything except the last one, which is probably not acceptable for most people. So the answer is yes, not immediately, and we'll probably have some discussion also with the community about how it looks like.
Yes. Thank you for that. And meanwhile, just so that everybody sees, by request, I put the exact command line text to put into DIG to get your label back into the chat window. So you've got that. And that was the last question. So I want to thank you all very much for your time. And again, if you pay attention, you'll get an email when we have a recording of this session posted to the website. Have a great day.
Thank you, everybody. Take care.